All right, so let's take a look at the next section, which is the power triangle. So the power triangle is basically a representation of a right triangle showing the relationship between active power, reactive power, and apparent power. So if you look at these two images or diagrams of the power triangle, you can see one of them is pointing up, and the other one is pointing down. These indicate the two versions of a complex power that we can have. So we can have an inductive load, which means that the current is lagging the voltage, and therefore the uh, the reactive power is more inductive. Or we can have a capacitive load, which means that the current is leading the voltage, and so therefore the reactive power is negative. So if I were to write this out in like a formula, something like this. Actually, look something like this. S equals E plus L Q, and post over here you have S equals P minus J. All right. All right. Moving on. So down here at the bottom, you have all your power triangle equations that you need to solve for any one of these terms. So if you are given at least two of them, you should be able to calculate the remaining terms. So you got four terms that you can find: the phase angle, the real power, the reactive power, or the apparent power. So if you have two of these four, you should be able to find the other two by using these equations down here. All right. So here's an example. A load has the following parameters. You have the real power equals 5 kilowatts. The reactive power equals 1.5 kilovars. I want you to find the parent power, the phase angles. I want you to write the complex power in polar and rectangular form. So to find the apparent power, we just use the Pythagorean theorem. And once you plug it to the formula, you get 5.22 kilovolts amps. Now from there, you can find your phase angle. And you could have used any one of these formulas up here on this right side to calculate the phase angle. I just chose to use this one that has the inverse cosine. And so once you plug into the formula, you get 16.69 degrees. All right. And so to find your complex power in polar form, I mean, you pretty much already did the work. So you got your magnitude coming from here. Um, all I'm really doing is just plugging that in. And also you already have your phase angle, which is all in right here. You already did all the work. All right, so from there, I want you can simply just calculate the rectangular form of the complex power, which is pretty straightforward because I already given you the real and the reactive power. So all you have to do is just plug them into this form right here. All right. All right, moving on. And so now for the next part, what I want you to do is I want you to use your calculator to kind of do the work for you. Make sure you are understand how to enter these numbers into your calculator to convert it from pole to rectangular and vice versa. So if I were to plug this into my calculator, the entry would look something like this, where you have 5 e to the 3 plus j 1.5 e to the 3. And that's just my reactive power. And once I hit enter, depending on the mode that you have your calculator in, so you should already have your calculator in the polar form for your output. And so once you hit enter, it'll spit it out in polar form. All right, so the next section is the power factor. So in AC circuits, the power factor is the ratio of the real power that is used to do work and the apparent power that is supplied to the circuit. The power factor can be represented as percentage or a decimal. So therefore, the power factor will have the value in the range from 0 to 100% or 0 to 1. All right, so the closer the power factor is closer to unity, which is 1. So in other words, the closer the power factor is closer to 1, the more efficient the power is being supplied to the load. And this sheet actually says more efficient the apparent power is being supplied to the load. If a power factor equals 1, then the reactive power Q will equal 0. If the apparent power and the real, also the apparent power and the real power are equal. So in other words, if I were to draw this out in like a power triangle, and compare the two triangles, I had one that looked like this versus one that looks like this. So as you can see, as the phase angle gets smaller and smaller, the apparent power that's being supplied to the load starts to equal more and more like the real power. All right, so I hope that makes sense. But there are a few ways to calculate the power factors. Listed below are the main equations. And so you got power factor equal to cosine of theta. We've already talked about that one. But a lot of people forget about this one. Power factor equal to cosine of the angle of the impedance. A lot of people forget about that one. So if you have something like this, if I give you a load that says V equals, um, let's say 20 with a phase angle of 40, guess what? You already have your phase angle. You just plug into this formula right here, get the cosine of it, and you have your power factor. And then lastly, power factor equals the real power over the apparent power. All right, so that's it for this section. Coming up, we're going to talk about power factor corrections. See you next video.